Some time, shall we start our session? I will give a short introduction before start the real presentation. So good morning, good afternoon, or good evening, everybody. Thank you for joining us. And we would like to start session emerging technologies and their applications from the depths of the ocean to the deep Antarctic field and space. And we have 11 submissions for this session. And conveners are Takashi, Yamanouchi, myself, National Institute for Research, Japan, and Francis Bennet, Australian National University, and Kimberlee, Baldry, University of Tasmania, Australia. So, just as for the points, we have 2 hours block from 9 to 11 standard time, contains 8 oral presentations. We keep 15 minutes for each, but I wish you to use 12 minutes for the real presentation and maybe 2 minutes for questions after each presentations and another 1 minute for changeover. And also, as already announced, the session will be recorded to be made available to registered participants in the past event section and also uploaded to the SCAR YouTube channel. So if you do not want your presentation to be made available on your YouTube, you should reach out to SCAR 2022 by 12th of August to opt out. And also, please don't forget to visit ePoster at the exhibition space on the event platform. We have 3 posters for these sessions. So let us start the presentation. The first part will be shared by Francis Bennet, and the second part with Kimberlee Baldry. So please start, Francis.
It's the other way around. Kimberlee's going first. Go ahead.
Oh, Kimberlee.
Thanks, Francis. So first up, we have Peter Sapunjev, who will be giving a fantastic talk on a comprehensive modeling of a standalone power supply system for field equipment for the Antarctic region. So I really hope to hear how this is important, because I can imagine power supply is a very important issue in Antarctica. So go for it, Peter.
Hello, can you hear me well?
Yes.
All right, I'm going to share my screen and to start my presentation, all right?
Yep.
Okay. As I've been introduced, my name is Peter Sapunjev, and I work with the Bulgarian Antarctic Institute, also with the Bulgarian National Institute of Geophysics, and I've been part of the Bulgarian Antarctic expedition for 5 years now. So the Bulgarian, well, in this presentation, I will talk briefly about our struggle and our success with providing reliable power supply for our field instrumentation in the area of the Bulgarian Antarctic Station. And I will start with the presentation. Just a second. Well, the Bulgarian Antarctic Station is located on Livingston Island. Livingston Island is part of the South Shetland Islands, and as I guess most of the Antarctic research facilities, so some of our main work at the base is installing and working with field scientific equipment for gathering all kinds of data. These are just some examples of the field instrumentation we have at our base. These are a permanent GNSS station, meteorological stations, some video monitoring equipment. We have a permanent seismic station. We also have communication equipment, and each year we add to the variety of equipment we use at our base. The Bulgarian base is a summer station, which means that at the end of the summer season, we close the base, and we hope that all our instrumentation works reliably during the winter season, because there is no one there to maintain and to take care of the equipment. And the most challenging aspect of designing field instrumentation for us is to provide reliable power supply. We mainly use solar power and battery storage, but as you can imagine, during the winter season, the solar irradiance is very scarce. So here is a general structure of field instrumentation system. We have the solar irradiance as an energy source. We have some photovoltaic solar panel. Then we have the electronics that takes care of the energy from the photovoltaic solar panel and charges a battery. It could be lead battery, it could be lithium-ion battery. Then we have some power converter, which takes care of adjusting the parameters of the battery energy to fit with the requirements, with the power supply requirements of our instrumentation. So this is the general structure, and this is a typical example of a field instrumentation we use at our base. So we have the photovoltaic, we have some solar charger controller. Sometimes we use PWM controllers, sometimes we use maximum power point tracking devices. Then we use, mostly for our field equipment, we use lead AGM batteries. They've proven to be, along with the lithium-ion batteries, they've proven to be the most cost and temperature efficient batteries for us. Then we have DC power converter, and we have an example of scientific equipment. In this case, this on the picture is shown the digitizer of our permanent seismic station. So in order for us to design a reliable power supply for our instrumentation, we found generally two approaches. One approach is to highly oversize the power supply, which means we put huge batteries, we put huge solar panels, which has proven to be not very efficient, because most of the times our equipment is installed in remote locations, so the access is not easy. Usually there are even some places we literally cannot carry all the equipment because we have to carry it on foot, on glaciers, peaks, mountain peaks, and at some point we found necessary to find a way to precisely design and estimate the requirements for our power systems and to size them down as much as possible. To do that, we decided to create a simulation tool, which is mostly a set of equations that, and each set of these equations model each part of the whole system. In the table on this slide, there are most of the parameters that we use to model each one of the components of our system. As you can see, we model the transfer function of the solar panel, then we take into account all the processes, electrical processes happening in the charge controller. The most delicate part are the batteries, because the batteries are the most susceptible to temperature component in our designs. It turns out that, well, we contacted a local research lab that investigate thermal processes in batteries, and they're giving us very useful information for the temperature processes in the batteries. And the batteries are the most delicate component to model, and it turns out that at the temperatures we use in the batteries, sometimes we can use as much as 25% of the rated capacity of the batteries, and this depends on the changing conditions of the environment. Well, on this slide, you can see year-long data of the solar irradiance, and as well as a year-long data of the temperature in the vicinity of our base. Those are daily values, they're averaged. Of course, there are spikes, but for our design, this is more than enough. And as a time precision, we use those. We use the curves provided by the solar panel manufacturers in order to approximate the transfer function of the solar panel, which mainly gives us the output of the panel, the electric output of the panel with a given solar input. Then we model the thermal processes in the solar panel using the input, the temperature input data as a reference. And as I already mentioned, we take into account thermal processing batteries. We take into account all the internal consumption of all the components in the system. And
so 2 minutes.
All right. In the output of our system is hourly and daily values of the state of charge of the battery. By having the state of charge, we can estimate the energy we have stored in the power supply system. So these are example of one setting of the power supply, how it will perform with different with different equipment, and it's just demonstrational. It clearly shows that some of the equipment won't work because just the energy stored in our battery won't be enough, and by tweaking the separate components of our model, we can much faster, quicker, easier define the components and choose the right components of our power supply system. As a conclusion, so far, this simulation tool has proven to be quite useful for our work. And also we found the necessity of building dedicated data logger in order to collect more precise data for the solar irradiance at different angles, which angles are defined by the land shaft at our base and by our possibilities to mount and install solar power system.
Right. Thank you, Peter. That was really, really great talk. We do actually have a question for you if you'll take it quickly.
Yes.
So from Matthew, he says,
right.
Thanks for the nice talk. Did you simulate both lithium ion and AGM batteries? And if so, which performed better?
Well, I'm in the process of simulating both. And the thing is that, as I already mentioned, we're in contact with a local research lab that mostly works with AGM batteries. So they can provide us a lot of information with the for the AGM batteries. For the lithium ion batteries, we don't have as much information, so we build our own test equipment. For example, we have those freezers where we put the lithium ion batteries and we cycle them thermally. I would say it depends on the application. If Matthew needs some more specific information, he can contact me. But for me, it's hard to say this one is better in general. Something just that we found that with the AGM batteries, because of the chemical processes in the acid, it's the safe range, the safe discharge range for the AGM batteries very much narrows with the dropping of the temperature. In other words, if you have like at minus 25 degrees Celsius, you can use like as much as 30% of the rated capacity of the battery if you want to keep it safe.
All right, great, thank you. So just lastly, can you confirm that if people want to ask you further questions or if they're interested in using your tool, they can contact you?
Yes, absolutely. You're welcome to contact me. This is my email on the slide. I'll be happy to provide and share experience with anyone.
Brilliant. And you can keep asking Peter in the Q&A and ask anyone any questions in the Q&A option, which is at the bottom of your screen.
All right.
So we'll move on to Yi Hu now, who will be presenting on an instrumentation of multi-layer automated weather station for atmospheric temperature inversion monitoring and astronomical site testing at Dome A, Antarctica. Very interested in hearing what this is all about. So take it away, Yi.
Yeah, thanks. So, can you see the screen?
Yes, sir.
Yeah. Hello, everyone. My name is Yi Hu. I'm from National Astronomical Observatories, Chinese Academy of Sciences. thanks to the conveners of this session, give us such an opportunity to express our experience on developing automated weather station at Dome A. Dome A is the highest point on the Antarctic plateau with the elevation of 4,000 meters. The environment is very tough. During the winter, the lowest temperature will be down to -80 degrees. Dome A is, until now, Dome A is still a summer station. So during the winter, there is no human being there. The power supply is given by Plateau A, but its total power output is only 1 kilowatt. So while we do astronomy in Antarctic, this is because the domes on the Antarctic plateau have the best astronomical site conditions. In our work, we focus on the free atmospheric scene. The scene is atmospheric effect. It can downgrade the quantity of images as shown in the right figure. Unlike Earth side on the Earth, the boundary layer at domes of Antarctic is very thin. For example, at Dome A, the boundary layer height thickness is only 14 meters. So it is possible to obtain free atmosphere scene above the boundary layer. For the testing, we need a multi-layer automated weather station to monitor the turbulence within the thin boundary layer. As such, we designed our AWS as this. It is a 15-meter tall mast with 10 temperature sensors and 7 anemometers at different heights. Although AWS is a very simple device in a normal place, but it's not the case at Dome A, because the most difficult is the very low temperature. As we know, there is no commercial product can guarantee at this low temperature. And even worse, the power supply is very limited and no human maintenance for a year. To overcome these difficulties, we carefully choose and calibrate our sensors and design the redundant policies and build active thermal control systems. We choose what the sensors we choose are from Young company. We also noticed that the temperature measurement range is only down to -50. So we send our sensors to the NIM of China to calibrate them. Sorry. This is the calibration results. We find that even below -50 degrees, the temperature sensor works very well. We also calibrate the anemometers. We find that the linear rating of the anemometers are very well, and so we use these temperature these sensors. We also developed the data acquisition system to improve the reliability, we employ 4 temperature sensor acquisition modules, 3 voltage acquisition modules, and we collect the adjacent sensors to different acquisition modules. So if one of the modules is broken, our acquisition system can still work. We also carefully design the thermal system. What the electronics are installed on the inner box. Between the inner box and the tail box, we filled with PU plates. The thickness of the PU plates are carefully calculated, and so that it can guarantee the inner temperature be 40 degrees higher than the outside. We also build active heaters, so they are regulated by the inner temperature sensor, and they can open and close on demand. Here is the results in the lab. As we can see, we can keep the inner box temperature between -10 to -20 very well. We also developed the data acquisition software, and this software can be downloaded via GitHub. The KLAWS was firstly installed in 2011, and we renewed them in 2015 and 2019. It totally collected more than 15 months data. It's released and available at our website. The scientific products are very fruitful. By analyzing the data, when the very strong temperature inversion just occurred above the surface, and we also find that when the temperature inversion happens, it can last very long, typically for 10 hours or more. The temperature inversion and the moderate wind speed implied Dome A has a stable atmosphere, and so have very good seeing. Furthermore, we developed equipment to directly measure seeing. We find out the median atmosphere seeing 0.3 arcsecond. Compared with the data from the AWS, we find the seeing has a strong anti-correlation to the strength of temperature inversion. So we derived at 14 meters, we have 50% chance to obtain free atmosphere seeing. Here is my summary. So we developed a multi-layer AWS, and it survived for a harsh environment at Dome A. It collects totally more than 50 months data. And we find that these data are very useful for our purpose. We're also looking for collaboration with other communities. And that's what. Thank you.
Thank you. That was a very, very informative talk. A lot of work definitely went into that. So thank you for coming to share. Just wait. We'll just wait a few seconds. Just if you have any questions, please put them in the Q&A. And if you don't, please try and contact Yi. He's very open to collaboration. So it would be good to see something come out of this.
May I have questions? I cannot log into Q&A, so Convenors cannot go Q&A. So what what is the strength of inversion layer in the winter time? You show that the thickness of the boundary is 13 meters or 14 meters, but what is the amount of inversion strength?
This, you mean?
So I mean the temperature, inversion temperature.
The figure, right
Largest.
side. Yeah, it's at 8 meters. It can be 10 degrees or more.
The 10 degrees or more, is it?
The boundary layer thickness is measured by sound radar, and we in the right figure that we can see the scene have strong anti-correlation to the temperature difference or the so we can derive the at 40 meters we have 50% chance to get free atmosphere scene.
So looking this figure, largest temperature difference nearly 20 degrees.
Yeah, the difference between 8 meters to surface can be as large as 20 degrees.
Okay, thank you very much.
Peter, did you have a question?
Yes, thank you. I just don't have access to I cannot type in Q&A section. Maybe first, thank you for the presentation, and it's impressive the work you've done. I just missed it. So when you have an active heating, I guess your equipment requires that. How do you provide what kind of power source you use during the winter months for that system?
Oh, yeah.
Thank you.
The power is from Plato A at this, and it's a diesel power generator, and the total power output is only 1 kilowatt. It's not a solar panel or other power. Yeah.
Thank you very much.
Yeah.
All right, thank you. Now we'll move on to our next talk. Thank you, E. Next up, we have Marcus Birch, who will be presenting free space optical communication for Antarctica. So welcome, Marcus. You can share your screen.
Yep, one moment. Can you hear me okay?
Yep, can hear you very well.
Great, thank you. Okay, so I'm Marcus Birch, as I was just introduced, and I'm a PhD student from the Australian National University in Canberra, and part of Mount Stromlo Observatory. And I work with one of our session chairs, Francis Bennet, in a group that works on free space optical communication, which is sort of an emerging telecommunications technology that we think has some real qualities that could fit the niche of telecommunications in Antarctica. So one moment. So I'll start by sort of explaining what free space optical communication, or FSO, is, It's sort of an attempt to combine the best of both worlds as far as the internet is concerned. Typically, the internet is either a wireless connection over radio waves or lasers transmitted through optical fibers. So FSO is when you sort of transmit your laser light as in a fiber through free space. And that allows you to have the bandwidth you would have through fiber internet, but obviously to either a satellite in space or, in the case of Antarctica, to a sort of remote station where you don't have a fiber link. But there are a number of reasons that it's obviously not as widespread as radio communication. One of the main ones is if you have any clouds, you can't communicate. So that's a really big problem. The stations themselves, which are traditional optical telescopes, are also somewhat more complex than standard radio dishes that are at most large Antarctic bases. So Antarctic telecommunications is obviously not great, and it's sort of well known that it's quite tough. Obviously, for a number of reasons, you can't have high-speed internet like we're used to in the rest of the world. One of the main reasons behind that is just because it's so far to run a optical fiber under the ocean. So the sort of high speeds we're used to are currently out of reach for Antarctica. There are some possible ideas being floated of running an optical fiber to Antarctica, but if that is ever done, it will be quite limited. But currently, communication typically relies on geostationary satellites, and that can provide quite a limited both bandwidth and only a few hours possibly in a day, or persistent internet that's very, very low speed. That's really can't meet the requirements that sort of the new big science experiments that might be deployed at the South Pole will really require. So there's a gap in capability between the internet requirements of large scientific experiments, such as IceCube at the South Pole, and really what can be provided by geostationary satellites. One of the possible solutions to that is these next-gen constellations, such as Starlink, but it's unclear really how the coverage will be over the poles. If there will be coverage over the poles, it'll be quite limited, and it's possible that the bandwidth will be very low. So free space optical communications offers intermittent internet. So this is not a sort of solution to allowing crew at bases to be able to stream Netflix, but it can provide terabytes to petabytes of data uplink and downlink per week that can be used to offload large data streams from experiments. So the reason we think FSO would work well for Antarctica, a number of reasons. One of the main ones is particularly for inland bases, the cloud coverage can be quite low. And as the previous speaker explained, the conditions for astronomy are very good. And the conditions for astronomy are sort of that you want overlap exactly with what you want for FSO. So there's a nice niche where the sites are optimal for optical communication, and there is a real need for the good internet. And unlike astronomy, these systems don't really care about whether it's daytime or nighttime. We can operate throughout the year, so we can provide sort of year-long coverage. And another really sort of important driver for FSO is the size of a satellite terminal to deliver high-speed internet can be very small. Currently, the geostationary satellites that can provide the sort of intermittent high-speed links for stations such as the South Pole or Dome C are large bus-sized geostationary satellites that have costed billions of dollars, launched by the US government or the European government. So FSO satellites can be small CubeSats, sort of the size of a loaf of bread or a coffee cup, and still provide gigabit links. So that's like a very important driving part of what makes this technology really exciting. And what we're sort of proposing as our group to try and push this idea along and really demonstrate that FSO can be an exciting sort of way to bridge the communications gap in Antarctica is a relay demonstrator. So there is a number of existing satellites, I'll get to in a moment, that could be downlinked over Antarctica to demonstrate the technology. And we plan or would like to do either a small portable ground station that's essentially a telescope, as you can see, at one of the Australian bases, such as Davis or Mawson, or adapting an existing small astronomical telescope at Concordia Station at Dome C. And using the existing satellites and either a current telescope or a really small telescope, we hope to be able to demonstrate a gigabit link to be able to offload sort of possibly terabytes per week, theoretically. So just briefly, Australia operates 3 coastal bases. So these would all be possible candidates for where we would deploy a portable optical ground station. And I've just done some work with satellite imagery to get a feel for how cloudy these sites are. And I'll use that later. I'll show you later how that comes into estimating the performance of these systems. The coastal sites are obviously a lot easier to deploy at than inland bases, which are logistically difficult, but the cloudiness is a lot worse and the astronomical conditions are a lot worse. But it could be an ideal place to start demonstrating this technology. So one of the really important things that makes FSO a really viable candidate for communications in Antarctica is that the orbital dynamics of sun synchronous or polar satellites really suits Antarctica, essentially. So a lot of communication satellites, particularly small satellites, and a lot of the existing optical satellites we could test with are in polar orbits. So essentially every single orbit, every 90 or so minutes, they'll pass over the poles, but they may not pass over a site closer to the equator, such as Canberra, where we are. So this is just to demonstrate this figure by simulating a year of orbits. Dome C, Concordia Station, gets over 4 times as many passes as Canberra for a given satellite. So essentially that means you have 4 times as much data as you would at another site. So that's a really, really fantastic part of this technology. And it means that if we were to select a site such as Dome C, which has very, very low cloud cover, that can couple to very high passes of satellites to give a sort of high value internet connection for really what could be a small payload or a slew of small payloads. And then, as with a lot of high bandwidth satellite communication, the data is uplinked to the satellite and then re-downlinked to sort of the more global network. So data that's uplinked to a satellite as it passes over an Antarctic station can be downlinked over Europe or over Australia, where there's 2 current planned optical stations, or probably in the future, there'll be a lot more optical stations. And that could be used to really offload large portions of data to give speeds equivalent to the rest of the world effectively. So I've just taken sort of the cloud coverage statistics for the Australian bases, or in this case, Davis Station and Dome C at Concordia from another paper, which I've forgotten to cite, and coupled that with estimated passes, and you can get a feel for how much data could be downlinked or uplinked, from one of these stations per week for a given satellite speed. So a single satellite, such as Tosiris, which is a very small satellite, about this big, could offload 2 to 2.5 to 7.5 terabytes per week. So that gives you equivalent data rates from a very small package that could be done quite simply to what is currently achieved with large multi-ton geostationary satellites that are put up by governments. Yep, thanks. So, and these sort of satellites, Tosiris and Biros that I've mentioned here, are existing ones. So the technology is progressing very fast. There are a number of new satellites, new and small satellites, that will try and push the speeds for optical satellites into the tens and potentially hundreds of gigabits per second. So we could foresee that petabyte or hundreds of terabyte links for large stations that really need that data because of scientific experiments could be met with just a small train of essentially CubeSats to really meet the sort of big data that we foresee coming off these stations in a way that probably can't be met by existing communications, and especially if there won't be a fiber link to Antarctica for a very long time, which is quite probable, especially for the sort of very inland bases.
Thank you, Marcus. Are there any last minute questions for Marcus to come through? Any of our co-conveners have any questions? All right, we might move on then. Very important work in the scheme of things with all the talk in Australia around Antarctic research and Antarctic data. So very exciting to see your work today, Marcus. Thank you.
Thank you.
All right, next up we have Darcy Barron, who has actually pre-recorded their talk. Is that you, Darcy? Have you joined us in person for questions?
It's the middle of the night and I'm traveling, so to keep to time, we'll play my talk, but I'm happy to answer questions afterwards.
Brilliant. Thank you for coming. So Darcy's talk is on science at the South Pole's dark sector and potential for interference from emerging communication technologies. So if IT could play that recording. Thank you.
Hi, I'm Darcy Barron from the University of New Mexico, and I'm going to talk about science at the South Pole's dark sector and potential for interference from emerging communication technologies. First, I'll start with the science. We're using the cosmic microwave background to study our universe. The cosmic microwave background, or CMB for short, is the afterglow of the hot Big Bang and is the oldest light we can see in the universe. With precision measurements of the CMB, we can understand our universe, including its composition and evolution to the present day. We can also use it as a backlight for all of the structures that have formed in the universe since its formation. The CMB today has cooled from its initial hot temperature after the Big Bang to a temperature of around 3 Kelvin. It still emits thermal radiation, shown here, across a broad range of frequencies, peaking in the microwave, or the millimeter wavelengths. What you might not realize is that in order to make the really precise, beautiful maps of the CMB, like what's shown here, we have to do significant work removing everything else from the picture. You can see some of these foregrounds to the CMB here, which are also really interesting features in our galaxy and distant galaxies to also study. We separate out all of these various components by measuring across many different frequencies. Typical measurement bands for a CMB experiment are shown here. The CMB peaks in brightness at 150 gigahertz, so we study in bands around that peak. This frequency range is mostly blocked by water and oxygen in the Earth's atmosphere, as you can see in the red line here, tracing out the atmospheric transmission at a typical site on Earth, Cambridge, Massachusetts. If you go to a really dry, high elevation site, like the South Pole, these measurement windows open up and the atmospheric transmission nears 100% in good weather. Because the Earth's atmosphere interferes with measurements we want to make, the best site for observing the CMB is in space, and several satellite missions have been completed to measure the CMB, including COBE, WMAP, and Planck. However, satellites are really expensive and technologically challenging. There are some things that just aren't feasible in space, like a 10-meter telescope. Fortunately, we have the South Pole, which is the next best thing and much more accessible than space. The atmosphere is extremely dry and thin and exceptionally stable because of the 6 months of winter when the sun is down. This stability is also critical for making precision measurements of the faint CMB fluctuations. The atmosphere isn't the only thing that interferes with CMB measurements. We are also observing parts of the electromagnetic spectrum that are heavily utilized for telecommunications, especially 1 to 40 gigahertz, which has many allocations for satellite communication. We refer to this as radio frequency interference. CMB instruments are extremely sensitive, but also extremely sensitive to interference. They generally use bolometers, which measure incident power from all radiation. This is unlike CCDs, which measure photons, or radio telescopes that measure the electromagnetic field directly, but this is exceptionally sensitive for this kind of signal and exceptionally sensitive in the microwave. Each individual bolometer has its frequency band defined by superconducting microwave structures. The frequency band fills each atmospheric window, as shown here, while avoiding atmospheric lines. The bolometer is sensitive to all incident power within this broad frequency range. In this broad window, a bolometer at the South Pole only measures a few picowatts of power total, coming from the atmosphere and the CMB. The CMB instrument can be vulnerable to interference even outside of this defined frequency range, but it is especially sensitive within the frequency band it was designed to observe. There are protections for radio astronomy in certain frequency bands, but modern experiments rely on measuring across broad bandwidths to achieve their science goals and sensitivity. You can see again the typical CMB bands here in blue, with protected spectrum in green. Each detector again observes across one of these broad bands, and we have many thousands and hundreds of thousands of detectors to build up our signals. If you look at a selection of CMB instruments, you can see the significant efforts taken to shield against stray radiation, stray power that could cause interference. However, these are still telescopes, and they can't be shielded against everything like some precision instruments. They must have an aperture open to observe the sky. Because of this vulnerability to interference, these CMB instruments are not just at the South Pole because of its exceptional atmosphere and stability, but also because they rely on its protections as a dark and radio quiet zone. The dark sector is deliberately placed away from the rest of the station, and during winter, when observations are taking place, it is typically devoid of any sources of interference. Radio frequency interference monitors have run continuously since 2014 and have helped identify and eliminate unexpected sources of interference. A growing concern for experiments that rely on dark and radio quiet zones to operate is the exploding population of satellites. This plot shows all tracked space objects in black and active satellites in blue, with both increasing exponentially over the past decade. The raw numbers can be hard to grasp, so there have been many visualizations of what the sky at night might look like once planned satellite constellations are fully operational. This one shown here is for the Vera Rubin Observatory, a large optical survey telescope, which would be impacted by reflected sunlight from satellites. You can see at the top left what the sky at night looks like right now, with the current satellites in orbit, and what this might look like in a few years after the full build-out. You can also see the satellite's orbits here shown on these lower plots. And I want to point out, well, there are over 2,000 Starlink satellites in orbit today, and many more going up each month. There are still very few in polar orbits, and not yet any that cross over the South Pole. These satellites transmit at microwave frequencies that overlap with CMB measurement bands, and they could overwhelm the sensitive CMB detectors that are designed to measure only a few picowatts of power at a time. We do have experience to guide us in what coordination and mitigation of interference from satellites might look like, balancing the needs of satellite communications at pole while protecting the significant scientific investments there. The current satellite uplink terminals are located about a mile from the dark sector, pointed near the horizon. Interference from these uplinks has been a problem, but one that we have solved with extensive mitigation efforts along with careful measurements, working with the NSF and the contractor providing these satellite communication services. The astronomical community is seeking to significantly increase our investment in the South Pole with the CMBS-4 project, which would observe with multiple telescopes at the South Pole to integrate deeply on the CMB for 7 years, reaching unprecedented sensitivities expected to transform our understanding of the universe. This project is under development now and will start observing at the end of the decade. It relies on unprotected frequency bands to reach its science goals, and it's hard to forecast what the state of satellite interference will be at that time. We hope by starting to think about this problem now, we can come up with reasonable solutions. Towards that end, we've written this paper recently that's posted on the archive. If you're interested in more details, please look at this paper with all of the details on these issues. In conclusion, the South Pole's dark sector is a really special place for astronomy because of its unique atmosphere, but also its extremely remote radio quiet location. RFI is something that radio astronomy has dealt with in the past, so we do have experience in mitigation techniques and coordination. We're seeking to significantly increase our scientific investment at the South Pole with CMBS-4, which has to make use of unprotected radio spectrum to measure the CMB. And interference from satellites is a really unique concern, since we cannot protect our instruments from it, and it can't be stopped with only local coordination. If you want to learn more about these issues in measuring the CMB, please read my recent paper. And if you want to learn more about the broader problems, see some of these resources that I've listed on the right. Thank you.
Thank you for pre-recording that, Darcy. Does anyone have any questions for Darcy, any of the co-conveners?
I just want to say we're really excited about technologies like Marcus's because they help mitigate these problems. The optical wavelengths can be much more tightly confined. The problem with radio is that if you want to talk to the pole, you illuminate the entire South Pole station. So optical technologies are really promising.
It was a really fantastic talk, Darcy. I understood everything at 10 p.m. at night, so it's good. Thank you. I might pass over to Francis now to move on to the next talk.
Thank you, Kimberlee. All right, so our next talk, I believe, is also recorded from Victoria Valdivia. Do we have that one ready to present from the IT team?
So we don't have Victoria's file. We have sent her an email. I haven't got any response yet. I request you if you could move on to the next one.
Sure. Okay. So I believe they were having some technical problems with her talk. So we've got Xiaopeng Fan next, who's going to talk to us about autonomous subglacial lake exploration. Xiaopeng, are you ready to go with your presentation? Okay, they don't seem to be there. Well, they may be expecting to start it in another few minutes. So what we will do, we'll start with one of the other, there are another 2 recorded presentations in this session. So in the interest of keeping things moving, let's go to Natalie Robinson's talk. Does the IT team have that one ready to go? Is that possible? That's great. Thank you.
Kia ora, everyone. My name is Natalie Robinson. I'm a physical oceanographer at NIWA in New Zealand. And today I'd like to share with you a new system that we have been developing for coring and sampling sub-ice platelet layers of the type that you can see here in the background image. Now, I'm representing quite a number of people and institutions here, but I'd like to make special mention of my colleague, Craig Stewart, who has designed this system. So just a wee bit of quick background. Platelet layers occur at the front of ice shelves where we've had ocean water getting in under the ice shelf, melting off the base, and having that meltwater escape the ice shelf cavity. So it carries with it fragile ice crystals in suspension, and those crystals will grow in the water because it's super cooled. The change in pressure from when that meltwater first formed deep under the ice shelf to where it appears at the front of the ice shelf has meant that without changing its characteristics of temperature and salinity, the water now finds itself below its own freezing temperature, although it's still liquid. So that allows these fragile crystals to grow to a point where they become buoyant and are able to precipitate out of the water column to land against the base of the sea ice above them. So in order to study this system, we've been working on the sea ice right at the front of an ice shelf. And of course, this allows us to access both the platelet layer itself and the supercooled water, and only need to get through 2 meters of solid ice. Of course, in some sense, you're asking for trouble when you put equipment into supercooled water because it's looking for a nucleation site. So here's some examples. And we're finding that we're having to deploy our instruments for a short period recover them, clean off the ice, and then redeploy them in order to collect good quality data. Here's just another example. This is overnight growth on a couple of our mooring lines. So we're working in McMurdo Sound. 2 images on the left, February at the end of the summer season, and on the right, October, which is what we come to when we come at the end of the winter season. So Scott Base is on Ross Island, and this red line here approximately identifies the front of the ice shelf there. And so you can see that in February, McMurdo Sound is filled with open water. It can be completely open water, as in this image, whereas in October, when we arrive to do our work, the sound is typically filled with sea ice, and in this case, it was a very extensive fast ice season. And so from there, we're able to access this flow of ice shelf water coming out from underneath the McMurdo ice shelf, but it's ultimately sourced from beneath the Ross ice shelf. So to do that, we pull our set of containers out from Scott Base, and they can be pulled behind a bulldozer out to site where they'll be put together into our field camp. Now, one of these containers has a generator in it, which means we can supply electricity to all of the other containers. But another special feature, on the left here, you're looking inside one of those containers, and you can see that white panel up against the wall at the back. It's actually a piece of floor that has been lifted out to give us direct access to the surface of the sea ice from inside the container. And then straddled across that hole that remains is a grid shape. Now we can place that grid down through the hole in the floor onto the surface of the sea ice, and now looking at the image on the right, we can pump hot water down through that grid shape, and it will melt its way down through the sea ice, leaving columns of ice that we can extract, and then we're left with a clean hole through the sea ice and into the ocean from inside the shipping container, so that we can keep accessing the ocean for weeks at a time and at whatever the weather. So I thought I'd show you a little bit of what this platelet ice actually looks like. So here's the base of the solid sea ice, and then underneath that we have this accumulation of these individual crystals that float up out of the water column to form this sort of complicated lattice structure. So in this case, you're looking at one of these holes in the sea ice. The top half of the image is the base of the solid sea ice, whereas underneath we have the very top of the platelet layer. So you can see these individual crystals right up against the base of the sea ice, and you can also see that there's quite substantial gaps for fluid in between them. Now in this case, this was a very clean platelet system with crystal clear blue colours. Conversely, the same season and only 70 metres away had another similar hole, but in this case it was completely loaded with algae. You can see that algae are attached to the base of the sea ice and dangling down into the platelet structure itself. Now, because all those crystals are there, and they can be several metres thick over just one season of growth, that has obviously essentially eliminated the ocean flow. So it's a very quiescent and protected environment. Nonetheless, there's enough light coming down through the sea ice to allow algae to thrive. There's also a high concentration of surface area for the algae to attach to. So what we end up with is quite a high concentration of primary productivity associated with the platelet ice, and that will make its way down through the platelet system and into the ocean below, where it can support the rest of the food chain. So I'm now part of a new study which seeks to understand the role that platelet ice has in supporting the ecosystem. So this is part of New Zealand's Antarctic Science Platform. Now, we already know that platelet ice has 2 major functions. As I just said, it has very high concentrations of primary productivity, in fact, the highest of any type of sea ice. And also, it has been observed in Terra Nova Bay to act as a silverfish nursery. So the silverfish, which are a keystone species of the Ross Sea ecosystem, will lay their eggs into the platelet ice, which provides, as I say, a quiescent environment, but also when those eggs hatch, there is a high concentration of nutrients available, and those eggs and larvae are also protected from their predators. So it acts as this nursery for that keystone species. So what we're wanting to do is look at the physical aspects of the platelet layer and understand how they interact with the biology. We want to understand how vulnerable the platelet layer itself is to potential shifts in the climate, and then from there predict what the knock-on effects for the Ross Sea ecosystem might be. As you can imagine, there's a number of design constraints. We want to be sure that we're retaining the physical structure of the platelet ice itself, and we want to capture the ice, the water, and the biology together in the same segment of the sample. And another interesting feature, we want to be sure that we can retain the base of the sea ice with the top of the platelet layer. So we want to capture that connection between the two. There are, of course, some issues with developing this, and these have been overcome. I'm not going to go into details on those, but of course, we're dealing with supercooled water, which wants to freeze onto anything. We're working down a small hole, effectively blind, looking 6 to 8 or even 10 meters below our feet. And we've got the issue of hydrostatic balance to overcome. So what I'd like to do now is play for you a short video. This was generated after our initial field testing season, which occurred in October last year.
This year we headed to Antarctica to test a new piece of kit that we have had specially developed in-house for coring and sampling a very special type of ice called platelet ice. There is more primary productivity associated with platelet ice than with any other type of ice in the ocean. So it obviously plays a key role and potentially underpins part of the food chain. What we don't know is how the distribution, the timing, the thickness, all of those things of the platelet ice itself might change if we're to see more general changes in the Ross Sea. This new system allows us to be ambitious with our science in a way that we just haven't been able to before. We're able to isolate them in situ without disturbing the structure, and then we can collect segments of that sample. We use our new drill system to drill through the sea ice, so we've got about 2.5 meters of solid ice to get through first. So we need a core barrel that's going to be long enough to get all the way from the top of the sea ice and then through as much platelet ice as we have underneath that. After we've isolated our sample, we have a couple of methods by which we can then draw that sample up through the core barrel and sort of siphon it off at the surface. A huge relief to see the whole system in action and to see that we could get every part of it to work. This new system opens a door for us to be able to get the new data that we need to understand the system as a whole and to be telling that story out into the future.
So I hope you enjoyed that. On the left here is one of those test samples that we have successfully collected. And you can see the platelet crystals in there amongst the ocean water. And then just to demonstrate, for the time being, this is how we've taken off the samples. So we can see that we've got a good structured sample, and then at the moment we're not retaining the structure when we take the sample away, but we are looking at ways to do that. But we can be quite confident that what we're collecting in the sampling chamber is a good representation. And here's one example that I was quite pleased to capture, where there are 2 distinct algal layers within the platelet structure, and these are separated by only about 15 centimeters. And you can see that through the sampling process, that structure has been retained with very little disturbance. So this gives us confidence that we're collecting what we think we're collecting. So where to now? So we have a main field season coming up this year in southern McMurdo Sound, and this will be followed up by a second science season, but that we're still shaping that at the moment. But the current season that we're planning for, of course, we'll be collecting vertical profiles of the sub-ice platelet layer using this new system, and there we're looking for physical structure and incorporated biology. We'll be collecting filtered samples of the interstitial fluid and upper ocean, And there we're looking for species presence or absence, or even abundance. There'll be a suite of oceanographic instruments that we have in use, and there we'll be looking for time series of structure and flow from the upper water column. We'll be conducting a snow survey looking for thickness, morphology, and microstructure. We'll be flying an ROV under the platelet ice, looking for the morphology of the platelet layer and also the light that's coming through it, both the intensity and the color, which can give us clues about the algae that are colonizing it. We'll be conducting surface-based, skidoo-based electromagnetic induction surveys, and this allows us to estimate platelet layer thickness over our grid, but from the surface of the sea ice. We'll also be collecting sea ice cores for a history of platelet ice incorporation and using an acoustic zooplankton fish profiler to get time series of suspended frazzle ice distribution. Unfortunately, I'm not able to answer any questions live for you today, but here are some places you can go to for more information, or you're more than welcome to connect with me on Twitter or to send me an email. Thank you very much for listening.
Great, thank you very much, Natalie. So Natalie's put her contact details there, so please get in touch with Natalie if you have any questions regarding this presentation. Really great to see some really ingenious instruments and designs answering some really important questions. So we'll go on to our next speaker. Xiaopeng, were you back and able to present now?
Yes, so I will share my screen now.
Please go ahead.
Yeah. Okay, so good morning or afternoon or night, everybody. My name is Xiaopeng Fan, come from Jilin University. So my topic is about Antarctic field tests of recurrence autonomous thermal sound, begin a new chapters in subglacial lakes exploration. So nowadays, it is generally recognized that a vast network of lakes, rivers, and streams exist hundreds and thousands of meters beneath ice. Latest, the global inventory identified 773 subglacial lakes in total, which include 675 from Antarctic and 64 from Greenland. So scientific drillings of subglacial lakes is a prerequisite for the research on the physical chemical properties and microbial characteristics of Antarctic subglacial lakes. 4 attempts were made by 3 countries in the last decade. So first is Lake Vostok. It's penetrated by Russia teams in 2012. And later, Lake Williams and Morse was penetrated into by USA teams. And the UK also tried to penetrate in Lake Ellsworth, but finally it's failed. Until now, only 2 technologies was development to subglacial lake sampling. And the first is deep ice core drilling technology is used for Lake Vostok. And when the drill penetrates into lake at depths of 3,769.3 meters, and the lake water just enter the borehole about 300 meters height. And later, the frozen lake ice samples were gotten by ice core drill. And these 2 figures showed, and when the lake water entered the borehole, it's just push the drilling fluid outflow from the borehole to surface. And the second picture is drill hand. It's covered by frozen lake waters. But some research shows that these samples contained inclusion of the drilling fluid with a concentration of at least 16.7 mg per liters. This makes it extremely difficult to obtain reliable data on the real chemical composition of the lake water. And the second technology is clean hot water drilling technologies used by BARS and the US. It's hot water was pumped into the borehole to melt ice and form the borehole. The drilling speed is quite fast, and the lake can be penetrated into in one Antarctic season. And it's more clear than deep ice core drillings because no drilling fluid in the borehole. Although the method of clean hot water drilling can avoid pollution to a large extent, there is still the risk of contaminating the samples and the subglacial lake due to the material exchange between the subglacial lake water and the hot water in the borehole. So in 2014, Pavel Tanlai suggests one technologies. It's called recoverable autonomous sound. And a unique features of recurse is that it can drill downward and upwards using bionic inner cable recording mechanism on the same way as a spider climbs on the slack lines. On the way down, so the lower melting tip is switched on. The melted water behind the sound will refreeze and seal the borehole. Thereby, the subglacial lake is insulated from the external environment, and the source of pollution is reduced as much as possible. So when the sound arrived the subglacial lake, and some sensors will be powered to measure the physical and chemical parameters of the lake water and sample the water. After that, and the sound will climb up and back to the surface by itself. So we are thinking this technologies is more environment friendly than the above two. So with the support of the Ministry of Science and Technology of China, and the prototype of recurse was designed and tested in the past 5 years. And our main purpose is penetrating into lake and get water samples not less than 200 milliliters. So here shows the structure and how the sound looks like. And on the top is the upper thermal hand, and then is winch is biggest part. And after that is the scientific platform, and the lower is the lower thermal hand. So the drilling ability of a prototype of the car sound is near 500 meters. And its penetration rate is 1.5 to 2 meters per hour. And here is the heating systems, because for thermal drillings, heating system is more important, and it concludes the melting tip. It's solid copper, and inside the copper bodies have some cartridge heaters. And on the top is aluminum cap to hold the pressure. And we also designed the lateral heaters. It will set along the length of recurse, because this heating will help to keep the water environment around the sound. Otherwise, the sound can stuck in the borehole. This page shows the inner winch. Actually, this is more challenging in our project because it's very difficult to design and install so small winch inside. And we compared several methods and finally choose the principles shows like the left figures. And it divided two parts. And the first is the cable climbing unit. And it's working like a capstan. It's two multi-groove valves. It will rotate, and then the cable will follow and pull the drill up and down. So its main advantage is it can reduce the force. So in the input side, it could be several hundred kilograms, but output only 20 or 30 kilograms. It will be more easy for drum designing because the strength we needn't so stronger. So This figure shows the structures. On the upper is a cable climbing unit, and in the middle is a control chambers. 3 motors was installed in, and then is cable core. So cable also is very challenging, and we can't find normal product to use in this case. And so we must keep the diameter of the cables as smaller as possible. At the same time, it should provide the power and the signals, and also the strength should be enough to hold the weight of the sand. And finally, we choose such structures, and the out diameter is 6 millimeters, and the braking force is 12 kilonewtons. In order to reduce the cable loss, so on the surface we use a high voltage power supply. It's near 800 voltage, and then directly powered to the downhole sound. And we also add the temperature sensors and the current and voltage sensors in the sound to monitor the working state of the sound. And all the parameters will transfer to the surface, and from the surface control interface, we can control all the parameters. So here is a scientific platform. Basically, it's confirmed the pressure sensor, temperature sensor, and pH sensor, and also electroconductivity. It's for lake water analysis. And we also have 2 samplers, and every one, the maximal volume is 360 milliliters. So after design that, we did a lot of testings in our ice wells. And this ice well is 1 meter in diameter and 12 meters in depth. And the lowest ice temperature can be -20. So it provides very good facilities to test the ice drills. And here is some pictures, and we drill down and drill up in ice wells. To prove it can work stably for long times, and we also running the winch in ice wells a very long time, and modify it, and finally the drill is fine. We also built the ice towers in Hongqi Lake, Changchun. So in winter times, just above the lake ice, we built 15 meters ice tower and penetrate.
2 minutes.
Okay, penetrate through it. And under the ice towers, it's 2 meter depth water. So we drilled 3 rounds, and every rounds get the water samples, and also send it to the third-party companies to check it whether it have big pollutions. Last seasons, and finally we got the chance to test our drills in Antarctic and near Zhongshan Station. So we chose the site is the blue ice areas on the flank of the dark glaciers, and the ice thickness is 200 meters, but it's a very pitch. Under this ice, no subglacial waters. It's just the frozen base. But anyway, 200-meter depth is enough to test the principles of the recurse. So this is the drilling process, and we install the mast on the sledge for easy moving. And also, here is a top view of the boreholes, and from the upper 10 meters, and the water can't hold in the borehole because it have some clearance and water just leaking. But lower, below than 10 meters, and the water can keep in. And totally 3 holes was drilled, and the drilling depth was 517 meters. And every boreholes we got near 600 milliliters water, but it's just the borehole melting water. It's not subglacial water. So the deepest borehole is 200 meters. So downward penetration rate could be 2.1, and upward is 3.6. And the borehole was sealed successfully by refrigerant waters. So we we're thinking the successfully testing provides the reliability of the new spider drilling approach for subglacial lake sampling and analysis. And this is also the first successful applications in Antarctic for this kind of subglacial environment exploration sound. So if consider for next plan, and firstly is about Greenland. We found under the fleet ice caps, it have a subglacial lake, and the thickness is near 600 meters, and it's very near the abilities of prototype recurse. So just a small modify, and we can use it here. And if for future for deep lakes, and China Ray also found a lake. It's about 3,600 meter depth, and for so deep lakes, we suggest better combine hot water drills and recast together. So hot water will penetrate the pilot holes and very fast, maybe in 1 week, and the rest 600 meters will drilled by recast, and in this case we can get the clean samples. Okay, thank you.
That's great, really fascinating. Thank you very much. Does anyone have any questions in the Q&A? Otherwise, do any of the other hosts or speakers have a question? Okay, no questions have come up, but I encourage you, if you do have questions, to please follow up. Oh, there's one. Okay, so we do have a question here. Do you plan to implement this at Vostok?
Until now, it's just some Russia researchers also discuss with us about these problems. And because now only recast prototype is produced and tested, so in the future for such deep ice subglacial lakes, and I thinking if combined with hot water drills is more efficient ways, so we can discuss in future maybe. Yeah.
Great, thank you. So I think we'll move on, and if anyone has any other questions, please feel free to send them through. So our final speaker is Svenja Halfter, who I believe also has a recorded talk. If the IT team could bring their talk up. Does the IT team have that talk ready to go?
All right. Hi, everybody. My name is Svenja Halfter, and today I present on the status of ocean observation in the Indian sector of the Southern Ocean. This work is actually an output of the Indian sector regional working group of SEUS. That's why you see the SEUS logo down there. And I'm currently based at NIWA in New Zealand. But I started this work when I finished up my PhD in Australia at the Institute for Marine and Arctic Studies. So the Indian sector, it's a really big area, kind of ranges from the southern tip of South Africa to Australia and Tasmania. It is an important region of Antarctic bottom water formation. And there's fisheries of toothfish and icefish and krill. And there's high productivity in the water, especially close to the islands because of iron fertilization and frontal dynamics. And climate change has already a huge impact on the sector because of all melting of the East Antarctic ice sheet. And as other sectors of the Southern Ocean, it is really connected to other parts of the world. If you're interested in more on that topic, please feel free to check out Eugene Murphy's review. So what is what's the current observing system, and what is an observing system at all? Because, it's probably a good thing to define that now before we start and dive into the topic. An observing system, in my opinion, is the integration of different sustained methods, for example, ship-based measurements, AUVs, floats, and satellites, but also modeling, that are integrated. And just the emphasis here is on sustained, just because it's not enough to go somewhere, have a one-off observation and measurement of something, and then never come back again. So we really have to start time series and repeat measurements to form an an observing system. It is usually an interdisciplinary and international collaboration, as most Southern Ocean research is anyway. And ideally, an observing system also includes some kind of platform or database to share data after the collection, or at least have a plan where to upload data. And even more ideally, you would have these plans even before you go into the field. Unfortunately, we don't start from scratch. There was a meeting of the Indian Sector Regional Working Group of SUS in 2017. And they had this workshop, and they defined the different regional interests of different countries that are involved in the research in the Indian sector, but also summarized the current efforts and current coverage of ocean observations. And this study I present today really focuses and is based on their efforts. We want to answer what observations do we really need to cover the main process and the most important drivers, and what are the spatial and temporal gaps. And this hopefully will inform future research priorities going forward. So I will walk you through now different ocean observations and different programs that have been in place for the different disciplines. I'll start with oceanography here, for example. And these are just examples of sustained measurements that have been made in the sector. So it's not a complete list. And if you're interested, feel free to wait for our publication that will be hopefully submitted soon and out, in the near future. But starting with oceanography and all kind of physical observations, we have the Argo float program. That is, these are robotic floats that provide year-round data. So it's pretty good for, to get a year-round view on the ocean. And now with the deep Argo floats, we also have a full water column profile, which is great. But there's a gap in ice-covered regions because the Argo float can't come up and send the data to the satellite. So we need to wait, during the winter, and hopefully they'll emerge in spring, sending the data. But then, of course, it's really hard to estimate where they have been under the ice. It's really hard to quality control the data. So there is a gap in ice-covered region. Then seals and other top predators have been used as autonomous environmental samplers that cover really extensive areas, and especially below sea ice, because that's where they dive sometimes. But this requires a high annual tagging effort because these tags fall off after a certain time. We need to go out there and tag the animals again. Here we go, there's a picture. And then, the most traditional instrument is CTD. There have been established transects in the sector, but the problem is in some years, not all of these transects can be repeated because the southernmost end is sometimes covered by ice. So without an icebreaker available or even an ice-strengthened ship, these transects can't be completed again, which is of course a problem. And overall, because it's a ship-based mission, these are really focused on the summer season when we have ships out in the region and it is accessible. And this is true not only for oceanography and physical observations, but also for all other observations. As soon as we have ship-based measurements to do, they are really biased towards the summer season, and we have a lack of winter data. For biogeochemistry, we have this amazing time series. It's from the Australian Integrated Marine Observing System, the Southern Ocean Time Series site, and has been established in 1997. There have been some earlier gaps in earlier years, but especially in recent years, we have a really consistent time series of different meteorological data, but also inorganic and organic carbon flux, nutrients, and biological production. And then we have the BGC Argo floats that are similar to the Argo floats, but have additional sensors, popped up. And they're a measure in addition to normal temperature and salinity like the Argo floats, also oxygen, pH, nitrate, fluorescence, and particle backscatter. Here we go, there's a picture of them. They look really similar, have just more instruments attached. And then we have the Go Ship initiative, again, ship-based initiative, which is a hydrographic survey and also takes inorganic nutrients and carbon profiles. And we have the GeoTraces program, which is focused on trace metal profiles. Again, both of them ship-based. That means we have most of the data we have are summer data. For the lower trophic levels, unfortunately, we don't have sustained observations of microbes. And it doesn't mean we don't have any measurements of microbes and microbial diversity, but we don't have a sustained observing system in place to understand microbial diversity in different regions of the Indian sector. For phytoplankton, it's a bit easier because we have remote sensing. Because of their pigments, we can see them in the water. Of course, satellites, again, come with different biases. You can't see through sea ice, you can't see through clouds. We can't see anything that's below the surface. So, for example, deep chlorophyll maxima, we can't see. And then we can't see in polar night. So again, biased observations. Then we have in situ measurements as well, for example, the floats, which measure fluorescence, but then need an algorithm to calculate in situ data. In situ chlorophyll. Ship transects, again, it's summer season mostly, and then we have SOTS. Here's a picture of a satellite measurement. And for zooplankton, of course, we have net collection of zooplankton. Again, it's really hard to find that. So we have the data, but you have to find the right person to talk to, really. And most of the data sets are in somebody's drawer, so just to access that is really hard. Fortunately, we have a thing called the continuous plankton recorder. There have been, extensive measurements with the continuous plankton recorder. It's a little machine we tow behind ships of opportunity, and this kind of, is towed through the water column, and we kind of record what kind of zooplankton is in the water at the surface. Of course, this comes with, again, biases, unfortunately. It is undersamples gelatinous plankton migrating in deep plankton because it just samples the surface. And again, because it's behind ships, it is focused on the summer season. That's how it is. That's what ship-based measurements have. This bias on the summer season. And for higher trophic levels, our monitoring really focuses on subantarctic islands and the continent close to Antarctic stations, and on colony-based marine predators. So, and also to come back to a colony at least once a year. Unfortunately, biologging technology have made huge advances in the last years. So now it is actually possible to tag animals and then integrate their foraging habitats to see where they find fish, for example, with information on physical forcing, which is great because, as I just mentioned earlier, they can go under the sea ice and measure physical properties there, and collect data for us. And we're currently at the stage, we are currently at the stage that we have lots of data, but we really need to integrate them. So we have lots of biologging data, and there's also long-term colony studies, monitoring studies. And what we need now is kind of integrate all of them together and make sense of the data. For the benthic communities, we have been making benthic observations since the Challenger expedition, really, but they're still relatively rare. There has been a shift from physical sampling methods to photographic surveys, just because physical sampling is more destructive, really, and photographic surveys, you can go again to the same site and see what has changed, really. The most comprehensive surveys probably currently are on Prince Edward Islands, but in general, there's really just individual surveys here and there, especially on the continental shelf, and they're really sparse and patchy. So it is currently difficult to set a baseline to project future changes. And when we look at anthropogenic pressures, there's fishing pressure is really focused on the islands and close to the continent. That's where the fisheries are. We have the Antarctic krill fisheries that was closed in the 90s, but then also reopened fairly recently. And of course, with an increase in fishing, there also comes an increase in bycatch. So all of this, of course, is managed by CAMLA, but the problem is, I guess, it's just an additional pressure we put on the system on top of climate change and natural changes anyway. And then plastics, there have been, there's just few studies, but there's no really long-term monitoring. And the same goes for pollutants and marine invasive species. And again, I say there's few studies, but it's not really integrated in any observing system yet. Microplastics. So coming up with the preliminary recommendations, because this is still a work in progress. We need to really focus on year-round observations to fill the seasonal gaps, especially in winter. We just lack winter data in most of the disciplines. There's a spatial gap in observations around the sea ice and in subsurface oceans. We need to fill that. And then we need to understand and also quantify the biases of the different methods and different gears that have been used in different, observing methods. Then we need to be better in integrating data and sharing that as well, at least metadata, because, especially as an ECR starting out in the field, it is really hard to define the data you need and to make any, to draw any conclusions. And then we need to focus on developing a system of sustained observations. So repeating measurements and going there again and, sustaining observations to establishing baselines and project future changes. So that's me. Thank you so much. And thanks especially to all my co-authors, because without them, it wouldn't be possible. This whole work, wouldn't be possible without them. And of course, the funding to SUSE and funding myself by NIWA. Thank you so much.
Great, thank you for that. So I did see Svenja's email address come up there. So if anyone has questions, please get in contact via those details. I was just going to check with the IT team to see if we had any luck with Victoria's talk.
Sorry, sir, we didn't get any video.
Okay, no problem. Thank you very much. Otherwise, Takashi, did you want to close the session?
Okay, thank you very much for attendance, and special thanks to chair and also to technical team. So please don't forget to visit poster presentation again. And we hope we could we could go on our research in the future. So thank you very much for all attendance. See you